parts of the cohomology at the places V in S. And we saw, using this duality machinery and this formula that we had for comparing orders of dual Selma groups, that these two groups in this exact sequence have the same cardinality as soon as the set S controls the Selma group. It says the Selma group injects into the local conditions at those primes. And so then, since our ultimate goal was to bound this group, which is the kernel of this residue map, well, we saw that we had therefore transformed the problem into one of actually controlling the co-kernel of this map, which is a little bit more concrete maybe, because now it's turned into a construction problem, a problem of finding enough cohomology classes in the relaxed Selma group so that one can bound the size of the co-kernel. And our ultimate goal, remember, given the statement of Colli-Wagens's theorem, is to show that this co-kernel is at most one-dimensional over Fp. So that's what we're trying to prove. And we did this by actually constructing some classes using Heegner points. Okay, so we had these classes kappa of L, which were constructed using in terms of Heegner points. Okay, so I remind you that we had a class which I called kappa L bar, which I defined by the formula, 0 maybe, which I defined by the formula kappa L0 bar of sigma is just sigma minus 1 of a certain point, depending on L, divided by P. And this point was constructed from Heegner points by taking the basic Heegner point P sub L, defined over the ring class field of conductor L, and applying to it certain group ring operators defined by Colli-Wagen. So there was this DL operator, then followed by D1. And the main point about this QL is that it belongs to the Mordell-Weil group of E over HL, but modulo P, it's actually invariant under the action of the Galois group of HL over K. So that this really makes sense, and we saw that this E of HL is uniquely divisible by P, so that there's a unique point with this property in E of HL. And then, starting with this class, we kind of looked at its inverse image under restriction under the Kummer map. So we produced a cohomology class kappa of L bar in H1 of K E P torsion by, and then after that, from that we just took a lift. So kappa of L was just a lift of this class to H1 of K E with the P inside, where you just use the Kummer sequence, the cohomology sequence arising from the Kummer sequence to lift this class. Okay, so this is sort of where we want to be, because we're trying to make classes in here, right? Well, so it's not quite. We're in this Selma group is a subgroup of this global cohomology group, so now we have some global classes, and now I want to kind of write down the basic properties of these global classes, okay, that make the proof work. So, yeah.
These operators, D1, DL, so on, is there a right
Sorry.
reason in finding them, or is this just a result of the long search?
You'd have to ask Colli-Wagen that. I think Colli-Wagen worked for a long time on this. No, I mean, I don't know if Popescu is in the room, but if you ask Popescu, yeah, Popescu is.
They have something to do with the shape of the Euler factors in the function. I can explain this.
I mean, there is a certain philosophy around these operators. I mean, I think I don't know. At the time when I first learned about Colli-Wagen, I was a graduate student, so it seemed kind of out of the blue, right? But if you there's also relation with sort of derivatives of mod P analogs of L functions in a sense. So this is sort of a good, with the benefit of some hindsight. I mean, you can kind of, but okay, I won't attempt to do that. But to talk to Popescu after the talk. Okay. So yeah. So the main theorem about these classes is that. Okay. So these are the main properties that Colli-Wagen establishes about the classes kappa of L. The first one is that this kappa of L actually belongs to the relaxed Selma group at L. So it lands where we sort of want it to land. It has its ramification is concentrated at the prime L. Okay, so that's already a good thing since we're trying to make classes of this sort. The second property is that we can explicitly control the residue residue at L of kappa of L. So, okay, this class belongs to the LV at all primes except the prime L. And we, of course, want to sort of control its image under the residue map. So we have a criterion when this residue is non-vanishing. Now, I mean, I should have maybe said this, that if L is a Kolyvagin prime, you can compute the dimension of the H1 singular of KL EP. So this is a finite dimensional FP vector space. And the dimension of this is equal to 2. It's also the dimension over FP of the finite part of the cohomology. And you see, I mean, we saw before, so the local cohomology group is 4-dimensional, and you have this maximal isotropic subspace, H1 finite, which is 2-dimensional, and the local state duality identifies this H1 finite with the dual of the quotient, which is H1 singular. So two-dimensional vector spaces in perfect duality with each other. So you can, so okay, I mean, so if you know something about this residue, you're sort of saying that this image is going to fill up a certain piece of this two-dimensional vector space here. And the criterion is this residue is non-zero precisely when the point pk, the Heegner points, is non-zero in E of KL modulo PE of KL. So if locally at L it's not divisible by P, then you get a class with non-trivial residue. Okay, so that sort of tells you that these classes are completely controlled, in a sense, by the Heegner point that we started with. And then the third, okay, so now you see this residue is landing in this two-dimensional vector space, but you actually have an extra structure, which is the action of the Galois group of K over Q. And since L is inert, that sort of, there's the Frobenius at L, which corresponds to this complex conjugation. And so this action splits this two-dimensional vector space into two eigenspaces, a +1 and a -1 eigenspace. And the third property tells you in which eigenspace precisely this residue lands. Okay? And the thing is that the residue at L of kappa of L belongs to, okay, so it belongs to the singular part of this cohomology. It belongs to the minus epsilon eigenspace, where epsilon is a sign which is defined by the property that epsilon f equals the Atkin-Lehner at n evaluated at f. So another way of saying that is that epsilon is the minus the sign that appears in the functional equation for L E over Q S, for the L function of E over Q. Okay. Okay, I'm going to give you only a bare sketch. I mean, so the proofs of these things are calculations. Once you have the definitions, you sort of have to calculate. The first property isn't too surprising, because the class kappa of L was constructed by considering a point, namely this QL, which is defined over this ring class with the conductor L. That is ramified only at L. And so if you analyze the principal homogeneous space, which corresponds to this H1 of K EP, you'll see that it acquires a point over this ring class field. And therefore, because all the primes are unramified except L, it's locally trivial everywhere except possibly at L. So the proof of the first property is that, yeah, I mean, let's see. So this is really because this extension HL, the ring class field over K, is ramified only at L. And by their very construction, these classes become trivial when you restrict them to this ring class field. The second property is a calculation. And, okay, I still want to give it to you. So if I look at the residue at L of kappa of L, okay, well, how can I tell whether this is non-zero? Well, I have to look at its restriction to the inertia group at L. But you see, this the extension HL over H is totally ramified at L. So the generator for that Galois group, the global generator, which I called sigma L in my last lecture, is also a generator for the inertia group. So we just evaluate this class on this generator of inertia at L. So we just consider, so this is non-zero precisely if the class kappa of L evaluated, or I mean, sorry, I should say the class kappa bar, the one that I constructed before lifting to H1 of KEP. That's the one, so this one, this kappa of L bar, is the one which is kind of giving you whether the class is ramified or not at L. So you have to look at this kappa of L bar and evaluate it on sigma L, which is this generator of inertia. And you want this is non-zero in E of KL modulo P. Okay? And then, okay, now you just calculate. So this is just sigma L minus 1 times dl N1 PL divided by P. And you want this point to be non-zero in this quotient, E of KL mod P. And now we did this calculation last time when we studied the sort of invariance properties of this point under the Galois action. We find that this point is just NL times N1 P sub L divided by P minus AL times PK divided by P. And it is non-zero in E of KL mod P. Okay. So now I realize why. So yesterday I had something in my notes which I didn't remember why I wrote it. And so I suppressed it, and now I see why I needed it. So I remind you that in my notes, I mean, yesterday when I talked about the choice of the Kolyvagin primes, I imposed conditions on L which were in such a way that NL and AL were both divisible by P. So these ratios are nice integers, right? But what I had written in my notes is I wanted some extra properties of Kolyvagin primes, which are not usually imposed, but which simplify this computation. And the extra properties I wanted is that actually P squared divides L plus 1. Hence, P squared divides NL. Okay? And I also wanted to ask that P divides exactly AL. Okay. So I impose these more precise congruence conditions on L. Now, the same kind of Chebyshev argument that I kind of outlined last time, which I, anyway, was very sketchy on, allows you to impose these more precise congruences. So if you restrict the notion of Kolyvagin prime to this particular congruences, then this expression just becomes a unit at P times PK. So PK times AL over P is non-zero in E of KL mod P, and then that's true precisely if PK is non-zero in E of KL mod P. Okay, so if you just amend a little bit the definition of Kolyvagin prime so that these two congruences are satisfied, then you get this kind of cleaner statement. Otherwise, it's a little bit more complicated.
The exercise you gave yesterday in this more refined version, what is the exercise? The exercise was with Frobenius et al. This complex multiplication.
Yes. And so it'll be a little bit different then. Yeah. It'll be a little bit different. I mean, you have to impose a Chebyshev condition in the field cut out by the points of order P squared, and you need to impose that the Frobenius is complex conjugation in the field cut out by the P division points, but something a little bit different from complex conjugation in the larger field cut out by the P squared division points. Yeah. So you don't want the eigenvalues to be 1 and minus 1 there. I should say that this is just a small simplification. I mean, Kolyvagin in his argument doesn't impose that, and one could do without. One could sort of prove a similar formula for all Kolyvagin primes. This is just to make the life a bit easier. Okay, and I'll leave it at that. So for the third, maybe I'll leave this as an exercise, sort of to analyze how complex conjugation behaves on these classes. And then, so the last thing I need is I also need further classes. So I also need classes depending on two primes, kappa of L1, L2. So L1 and L2 are two Kolyvagin primes, and I look at a product of them. And I do the same construction as for the classes kappa of L, except that now I use the point which I call QL1, L2. And this one, I take the Heegner point of conductor L1, L2. So I now look at the Heegner point, which is defined over the ring class field of conductor L1, L2. And I apply the same kind of Colli-Wagner operators, this norm and DL1, DL2. I take a product of these two Colli-Wagner derivative operators. I think of this as an element in the integral group ring of the Galois group. And the same calculations I did before will show that this is invariant under the whole Galois action modulo P, and therefore you can use it to make a cohomology class. So you have these classes depending on 2 primes as well, and you have a result which is very analogous to this one that I outlined above. So you also have a theorem that says that, firstly, kappa of L1, L2, as the notation suggests, and as you would expect, because now I've constructed this class from a point defined over a class field which is ramified at 2 primes, L1 and L2. This one now belongs to the P-Selmer group of E over K, relaxed at L1, L2. So I've relaxed the local conditions at those 2 primes. And I can control the residue at L2 of this class kappa L1, L2. This residue is non-zero precisely when the restriction at L2 of kappa of L1 is non-zero in the H1 finite of K L2 EP. So the singular part of the class at L2 is controlled by the image of the previous class, so to speak, at the cohomology locally at L2. And then the third part of the proposition, which really justifies introducing these extra classes, is that you see here, with the classes depending on 1 prime, they were all landing in a systematic eigenspace for the action of complex conjugation. So you're only going to fill up half of this direct sum of H1 singular, since each piece is a sum of 2 eigenspaces for the eigenvalue 1 and minus 1. But so then the great thing about these classes is that they land in the other eigenspace. So these kappa of L1, L2 belong to the H1 of K EP, but they belong to the epsilon eigenspace. So you get a change of sign. And so now you can hope to prove, to sort of control the co-kernel using this collection of cohomology classes. And that's really what Colli-Wagner does. So now I can kind of give the proof. I can sort of complete the proof of Colli-Wagner's theorem. Okay, so we're going to use sort of a following kind of control lemma, which is going to tell us that we can control the Selmer group by a collection of Colli-Wagner primes satisfying some extra conditions which are cooked up so that we're going to be able to fill up the co-kernel with these classes, right? So the control lemma says this. There exists a set, a finite set, S equals L1 up to LT of Colli-Wagner primes with the following properties. So the first property is that S controls the P-Selmer group of E over K. So you can already see that a priori, we know this group is finite. So we're going to need to choose at least as many primes as roughly as the rank of the Selmer group of E over K. Okay? So we can do that. And then the second property of this set S is that the image of the Heegner point, the basic Heegner point pk, in E of k Li, the completion at Li, modulo p, is non-zero. And you can see why I would want a condition like that, given this theorem, right? And then the third is that if I look at the class kappa of L1, okay, so I take the class corresponding to the first prime in the set, and I look at the restriction at Lj of this class, that this is not equal to 0 for j equals 2 up to t. So that's my control lemma. And the proof, I'm going to be really glib in my proof. I'll just say one word, which is Chebotarev. It's not a completely trivial application of Chebotarev. You have to do a bit of work. But you can see how this kind of thing would follow from Chebotarev. Maybe I'll say something a little bit more. You want to apply Chebotarev to what? Applied to the field which you get by adjoining to K the coordinates of the p-squared torsion points of E. Dividing the Heegner point pk by p. Now, here's where actually my assumption that pk is not divisible by p is important, right? Because, well, if pk was globally divisible by p, I could never get this to be non-zero, right? But so this is a non-trivial extension of this. And what else do I need? And the field which is cut out by so I choose a basis as FP vector spaces by S1 up to Sm, a basis for the P-Selma group of E over K. You see, so if I have an element in the Selma group of the P-Selma group of E over K, I can think of these guys by restricting them to the extension that I get by joining the P torsion points of E. So if I look at the restriction to K adjoined EP of these S's, these are elements in Hom of the Galois group of K EP into EP. So they correspond to finite extensions of this KEP. So you need to kind of look at the collection of all these finite extensions cut out by all the elements of the Selma group. So you apply somehow the Chebotarev, you find a good Chebotarev condition, apply to this big extension, and if you kind of do it right, so the key ingredient is Chebotarev. Okay? And now we're done, because we can now okay, so end of proof. So by property 1, by 1, what is 1? So as I said before, I have this exact sequence from the P-Selma group of E over K to the relaxed Selma group at this. So now I take this S. I'm going to work with that S coming out of the control lemma. And then I have the direct sum of the singular parts of the H1, KL, E, P, L dividing S, or some L in S. Okay. So the first step is to look at the minus epsilon eigenspaces for this. So if I look at the minus epsilon eigenspaces for this exact sequence, what do I find? Well, I have this collection of classes, kappa of L1, kappa of L2, etc. And I'll note that the residue at L1 of kappa of L1, or maybe I should say residue, period. So the image of kappa of L1 in this direct sum is going to be 0 everywhere except at the component corresponding to L1, right? So this residue of kappa of L2 all up to residue of kappa of LT are linearly independent over FP. Let me give a name to this map. Let me call it the residue minus epsilon. So I have T linearly independent cohomology classes. But this space, remember I told you it was 2T dimensional, but when I take a certain eigenspace, I get a T-dimensional vector space over FP. So that means that the co-kernel is trivial here. Therefore, the kernel is trivial by what I had before. So the co-kernel of the residue map minus epsilon, which is equal to the kernel, which has the same cardinality as the kernel, so is 1, right? And that tells us immediately that the P-Selma group of E over K minus epsilon is trivial. Now, that's consistent with what you would expect from signs in functional equations, because remember, this epsilon turns out to be the eigenvalue of Wn, which is the negative of the sign of the functional equation. So, for example, if the sign of the functional equation were minus 1, if this were minus 1, then you'd expect that the Selma group over Q has something. So the plus eigenspace should be non-trivial, right? But for the twist, you expect kind of a trivial Selma group. So that's what we're proving here. And then in the second step, step 2, you look at the images of the classes depending on 2 primes, kappa of L1, L2, residue of kappa L1, L3, and so on, kappa of L1, LT. So now you have T minus 1 elements, and these are also linearly independent because of this third condition, that the residue, the restriction at Lj of kappa of L1 is non-zero. That's what controls the image of these things under the residue maps. So these are linearly independent over Fp. And so that means that the co-kernel of the restriction of the residue map to the epsilon eigenspace has dimension over Fp at most 1. Because I have this t-dimensional space, I have t minus 1 explicit elements that I've constructed in there, which are linearly dependent. So the dimension is at most 1, but of course the dimension is actually equal to 1 because we already have something. So that means that the dimension over Fp of the P-Selma group of E over K, the epsilon part, is at most 1. But then, of course, we have equality because we already know a class in here, namely the cohomology class arising from the Heegner point. So we know that the Mordell-Weil group is rank 1. So that means that the dimension over it, so it's actually equal to 1. In fact, the Selma group, the P-Selma group of E over K, its epsilon component is generated by the image under the connecting homomorphism of the of the Heegner point pk. And that completes the proof of Colli-Wagner's theorem. Okay. Yeah. Yes. That was an assumption in Colli-Wagner's theorem. So I was proving this mod P version. So the theorem I was proving is that if the Heegner point is not divisible by P, then the P-Selma group is one-dimensional. Now, of course, if the Heegner point is divisible by P, we expect the P-Selma group to be bigger. And then we have to work a bit harder to control its size. So I did a kind of simplified version, which was enough already to conclude that the rank of the Mordell-Weil group is 1, which is the main conclusion we want, really. I haven't quite proven that SHA is finite because of this collection of more difficult primes to handle. Okay. But this gives the flavor of the argument. There, yeah.
So you use those like pairs of primes there. So does this have to do with again the order of finishing, how many primes you should choose?
Oh, you mean why am I sort of working with 2 primes?
Yeah, you just go that far.
So I just went that far, exactly. And that's sort of because of what Kartik was saying, that I put myself in a simple situation where P does not divide the Heegner point. And so the Selma group is one-dimensional. And you can hope there to control the co-kernel of this residue map by Colli-Wagner primes, by Colli-Wagner classes depending only at most on 2 primes. I need at least 2 primes because of this business with the eigenspaces. So if I only work with classes depending on 1 prime, I'm only going to get half of the Selma group. Okay? So I need this sort of 2 because of this thing that I didn't really prove actually in these theorems, right? These part 3s, where I say that these things land in specific eigenspaces, but they change depending on the parity of the number of primes. So that's just an artifact of the argument. But if you were trying to do something more fine, where you wanted to control, in the cases where P divides the Heegner point, you wanted to control the size maybe of the Selma group in terms of maybe the divisibility by P of the Heegner point, which Colli-Wagner does actually in one of his papers, then you would need classes depending on more primes. which are defined in the obvious way. I mean, so you can actually use those classes to obtain finer information about the structure of the Selma group. Okay. Okay. So I don't know if there are any questions, any further questions. Now I'm going to kind of switch to a different topic, or a new topic, which is more related to the last talk of yesterday by John Voigt, and that we're going to hear more about this afternoon in the lecture by Matt Greenberg. And this is, okay, so the question motivating this is we now see that we have this wonderful theorem for elliptic curves over the rationals, okay? So, but it depends on all this machinery. It depends on modular curve parameterizations, CM points on modular curves, Hegner points, and so on. Do you have a question? Yes. Yes, so PK is the rational point of the curve. So delta is this connecting homomorphism arising from the Kummer sequence from E of k mod P E of k to H1 of k EP. So this is the delta, the usual, the delta map that comes up in descent. That's a notation I introduced maybe 2 lectures ago. It's not, it's not this thing. It's not this is the residue, not to be confused with, okay. Yeah. Okay, so the motivating question now for the second half of my lecture is, okay, what about other number fields? I mean, after all, this is a summer school whose focus is really general Diophantine questions about curves. And last week when I explained Falting's theorem, we saw that it really wasn't a good idea, in fact, to think about curves over Q. If you do that, you're sort of tying yourself, you're putting yourself in too special a situation, and it's sort of much easier to give yourself the extra flexibility of proving the theorem over arbitrary number fields. And it's one of the beauties of Falting's result, that we have a finiteness statement which is over arbitrary number fields. So we would like to have a similar statement. I mean, Bertrand and Dyer for analytic rank 1 seems to be a more tractable statement. And so it would be nice to have a similar statement for elliptic curves defined over arbitrary number fields. But then the question becomes, does all this baggage that we carried, I mean, the modular curves, modular parameterizations, CM points, do these things generalize to other settings? And the answer is yes and no, I guess. I mean, so what I'm going to explain now is that if we have an elliptic curve over a totally real field, so now F is going to denote a totally real field, then to a large extent, the main ingredients we had in this proof of Colli-Wagner and in this in Gros-Saguier would appear to generalize for many elliptic curves defined over totally real fields. Not all, but many. So today I'll explain that a little bit and sort of recalling some of the notions that were introduced yesterday in John Voigt's lecture. So I want to say now what plays the role of modular curves and modular parameterizations in this setting of totally real fields. Okay. So, okay. What is that? Well, so Shimura curves. I'm going to give you a kind of very brief description of Shimura curves. So I'm going to give myself a set S. Again, so let S be a finite set of primes of places, I guess, places of F, or completions, which contains all the Archimedean places. All the Archimedean. So all the real completions of F are contained in this set S. So I should say that here, at this stage, we're launching into a completely new topic, okay? So this set S has nothing to do with the set S I had before. It's a sort of completely different order of ideas, okay? So let S be such a finite set of places, and assume that the cardinality, so such that the cardinality of S is odd. Okay? So you've seen many times already that if you have a set of places of a number field of even cardinality, then there corresponds to that even set of places, a nice object, which is a quaternion algebra, okay, which is uniquely determined up to isomorphism. So you can ask what corresponds to an odd set of places. This is sort of a philosophy or a kind of a slick presentation which I learned from Gross. What corresponds to an odd set of places? And the answer is a Shimura curve. Okay, so I'll sort of tell you. So here's a big theorem, big result. Well, okay. So there exists a curve, an algebraic curve, which I'll denote by xs, which is defined over F, having the following properties. And some of this we heard in John Voigt's lecture yesterday, and some not. So I'm going to summarize. So this is going to be the Shimura curve attached to the odd set S of places. So S could stand either for Shimura or for the set S that I've introduced. It depends on the finite set S, though. And so the following. So the properties are the following. Firstly, we have analytic descriptions of this curve at all the primes of S. So analytic properties. We have some uniformizations. So for all V in S, okay, let B, denoted by B sub S minus V, the quaternion algebra ramified precisely at S minus V. So this is now a set of places of even cardinality. So I have a quaternion algebra. Okay? I'm going to denote by R sub V maybe. Maybe R of V. I don't want to make you think it's a local thing. It's a global object. So it's an Eichler order. Well, so there are two cases. Either V is Archimedean or V is non-Archimedean. So it's an Eichler order, maximal order in this quaternion algebra if what? If V is Archimedean and it's a maximal OF 1 over V order in the same quaternion algebra if V is non-Archimedean. So what do I mean by that? Well, a maximal order is simply a subring of this quaternion algebra, which is free of rank 4 as a module over the ring of integers of F. Okay? And an OF of 1 over V order is simply a subring which is free of rank 4, which is an algebra over this ring, over the ring of V integers of F, and which is free of rank 4 over that ring, and is maximal for that property. So that's my R of V. Because I chose this V to be outside the set of ramification, I have also an embedding, which I'll call iota V, from B tensored over F with the completion of F at V into the 2x2 matrix ring with entries in FV. Okay, so I fix such an identification. And then I'll write a gamma of V for the image of the set of elements of reduced norm 1, the multiplicative group, under iota V. So this is a subgroup of SL2 of FV. And then the statement is that we can identify the CV points. So let me write CV for the completion of the algebraic closure of FV. Okay, so that's sort of a complete algebraically closed field which contains FV. So it's a natural domain in which to do sort of P-Adic analysis. So of course, CV is just C if V is Archimedean. Otherwise, it might be a slightly more exotic object. And then the final statement I wanted to make is that, okay, so gamma of V acts on an object which I'll call the V-Adic upper half plane, which is simply it's simply P1 of C minus P1 of R, on which I take the things with strictly positive imaginary parts. In the classical case, if V is Archimedean, and it's P1 of CV minus P1 of FV if V is non-Archimedean. So it's sort of an analog. It's a non-Archimedean analog of the usual complex upper half plane. And the action of this gamma V on this thing is via Mobius transformations, thanks to the, so gamma V is a subgroup of SL2FV. So it preserves this, it acts on this, and it preserves the deleted set. And the point I want to make is that this action is always discrete. It acts discretely on this space. And so the final statement in part 1 is that the set of points on XS over CV are identified analytically with the quotient gamma of V modulo HV. So this is as Riemann surfaces if V is Archimedean, and as rigid analytic curves, otherwise. And for those of you who haven't seen rigid analysis before, don't worry, I'm going to say a few words about that shortly. I'll kind of sort of develop enough, which is not much, that we need to understand P-Adic uniformization of Shimura curves and the talk of this afternoon by Matt Greenberg. That's the first property. So in fact, I'll be focusing on this later. So this is really the main topic I want to discuss a bit later. No, but I'm saying that there
always exists without any curve.
No, but the curve XS is defined over F as this global thing. And then I'm saying that if you want to understand its CV points for the V and S, you have a model which is a sort of analytic description of it as a quotient of some upper half space, some symmetric space, either complex or P-Adic, by an explicit group arising from a quaternion algebra. That's all I'm saying. I mean, yes.
Is independent from the XS. It always exists. I can find this quaternion for this and then try to...
Oh, yeah. So you could certainly write. I mean, this quotient makes sense as a Riemann surface or a rigid analytic curve. So if you take a finite set of S, you could certainly write down this collection of curves. The amazing thing, which is by no means obvious, is that there's a curve over F, which analytically is isomorphic to this collection of analytic curves, which are defined in terms of completely different quaternion algebras. This is far from a formal statement. So the fact that there exists a curve over F, right, I mean, is kind of an amazing fact, actually. The second property of this is CM points. Okay, so we have if K is a quadratic subfield of the quaternion algebra BS minus V. Okay, so I take this global quaternion algebra defined over F, and I take a maximal subfield of this thing. It's a quadratic extension of F, right? And so I give myself any such quadratic subfield such that if I take the points of K, and I look at its image under this iota V, so this acts on HV in the natural way, and I want that this has a fixed point. So this fixed point depends on this quadratic subfield, So I'll call it tau sub k. Okay, so as a fixed point belonging to HV, then tau sub k corresponds to a, well, so it gives a point on xs of CV, okay, because of the analytic description. So it's a point on this HV. Therefore, I can view it as a point on xs defined over CV. But in fact, this point is defined over an algebraic extension over, so corresponding to which is defined over an abelian extension of the field K. So this we saw a little bit of in John's talk in the context of the complex uniformization of Shimura curves. You could identify specifically these CM points as fixed points of certain maximal quadratic. So actually, it's an exercise to see that if you have such a quadratic subfield, an easy exercise, that such a quadratic subfield having a fixed point on HV is necessarily a CM extension of F. So note that K is always a CM, and that's why these are called CM points. Okay? Yes, there's a relation with the moduli description. And that's one thing I'm pushing under the rug. I'm not going to talk about the moduli description. But of course, the reason why, as John sort of also quickly mentioned in his lecture, the reason why we have such a curve, right, is that we construct it as a solution to, or as related to a solution to a certain moduli problem, and then see that all these properties hold. Maybe I should also, I'll say some words about these facts here. So here I'm just stating a collection of facts about these Shimura curves, and I'll kind of try to put them in perspective later. The third thing, which is not a theorem actually, but which is sort of the analog of the Shimura-Taniyama conjecture. And let me just underline conjecture again, because this is not a theorem as in the case of Q. It's still a conjecture, although many of the ideas that were introduced by Wiles and his school to prove these kind of statements would seem to extend to this, but there are some technical, so in general it's still a conjecture. And so the Shimura-Taniyama conjecture says that let E be an elliptic curve over F such that, of conductor with the conductor of E, n sub E over F. So the conductor in general is an ideal of the field F, I mean of the ring of integers of F. And the conductor should be exactly the product over the places of S which are non-Archimedean. Okay? Then the conclusion is that if you have such an elliptic curve, it appears as a quotient of the Jacobian of this Shimura curve. Then there is a non-constant morphism of curves over F. So I'll call it maybe phi sub E from Js to E defined over F, where Js is simply the Jacobian of this curve xs. So it's an abelian variety defined over F. So in the same way that elliptic curves over Q always appear in Jacobians of modular curves, elliptic curves over totally real fields are often coming up in the Jacobians of these Shimura curves. That's conjecturally, but a lot of cases are known. A lot can be proved in this direction. But I mean, there's a whole sort of very active area of research right now devoted to proving these kind of statements for many elliptic curves over many totally real fields. But the thing is still in a state of flux right now, and there are many technical conditions still to be placed.
What does it say when F is Q?
Well, I'll get to that shortly. It says something new even for F equals Q, because you could take a set of places, right, which... There is a conjecture. Yeah. I mean, this is kind of a silly statement, I guess. I mean, I shouldn't have called this a theorem. Maybe let me just call it a fact. It's a collection of facts about these curves. Okay. I don't want to, because I'm being kind of informal at this stage. These are sort of facts about the curve. And the third fact is that we have this conjecture, in which we believe very strongly that these curves appear in these Jacobias. And moreover, I mean, okay, this fits into a general philosophy, and we have tools to prove this in many cases. So it's not a completely intractable conjecture. Also, if I give you an elliptic curve over f, a specific elliptic curve, you can check by a finite amount of computation that this is true. Either you find that it's true or you find that it's false, and then it would be kind of amazing and people would be very interested. So that's sort of the status right now. And one might expect that in some future time, this will be completely proved, maybe. You know? I mean, there's been so much progress in modularity questions in recent times that it's not out of the question. That okay. Okay, let me just say one last thing about these facts, since I'm kind of collecting a bunch of facts about these Shimura curves. You might also be interested in supersingular points on these curves. So you could look at the supersingular points on XS in characteristic V, where V is not an S. So on XS over the residue field, maybe over, I don't know how to call it, over OF modulo V, where V is a place of F, which is not an S. And there's a description, a very explicit description of these supersingular points in characteristic V involving the quaternion algebra ramified at S union V. And I'm not going to say anything more about that, but just sort of this is sort of a nice symmetrical way of looking at the various properties. So in some sense, in describing this Shimura curve, all the quaternion algebras, which are at distance 1, so to speak, from the set S, are kind of involved in various features of the Shimura curve, and that gives rise to a very rich structure, which is very useful in arithmetic. So in some sense, this collection of Shimura curves is really much richer as a picture than just the modular curves themselves. And now I want to talk about, so I'm going to leave it at that. I want to talk about the main feature, which is really new. Maybe, okay, let me first say something about Dan's question. Okay, so if you take f equals q, so example, okay, f equals q, and you take s to be the smallest odd set of odd cardinality containing the Archimedean places, and be the set infinity itself. Well, you know, then xs. Well, in this case, I guess it would be just x naught of 1, okay? But then you could also throw in some auxiliary level structure. In John's lecture yesterday, we saw an example where f was q, and s was the set consisting of infinity, 2, and 3. So that was the Shimura curve that we saw yesterday in John Voigt's lecture. And also in John's lecture, we saw a case where f was q zeta 9 plus, which is a totally real cubic field, and where S was the set consisting of the 3 Archimedean places. And we saw some nice computations with that involving that Shimura curve, which is interesting because maybe some coverings of that could be related to elliptic curves over q zeta 9 plus. Okay, so that's it. What is it? Okay, so what I want to talk about a little bit is the P-Adic uniformization, which is the new structure which you discover. And I should say that these are big results, right? All these facts which I stated. And the analytic description of the Shimura curves is due to Shimura, I guess. I mean, who kind of first studied these curves for the complex uniformization, and to Cherednik-Drinfeld in the case where V is non-Archimedean. This is explicit analytic uniformization. And what I want to talk about now is this P-Adic analytic description arising from the theorem of Cherednik-Drinfeld. Okay? And the point I want to make, well, when you first see this, you're less used to rigid analysis than you are to complex analysis. And so this might seem a little bit intimidating. You have to learn a bit of more machinery. But it turns out that from a computational point of view, and since we were told also that there was going to be a strong computational theme in the summer school, it turns out that the P-Adic uniformization is a lot more tractable, seems to be a lot better suited to doing explicit calculations with Shimura curves than the classical complex uniformization. And I want to explain now a little bit why, and we'll be seeing more of that in Matt Greenberg's lecture this afternoon. So P-Adic uniformization. So for that, I'm going to stick, it doesn't really matter, I guess, but for definiteness, let me stick to the case where f equals q, and I'm going to have a set S consisting of a bunch of primes, and I'm going to suppose that P, I have a prime P which is in this set, and I'm interested in understanding this Shimura curve x sub S over CP as a rigid analytic curve over CP. So I first have to tell you what I mean by a rigid analytic curve. And as I don't have all that much time to do that, so I just want to kind of give you an idea, right? So we see that XS over CP is a quotient of the P-Adic upper half plane by a specific subgroup acting discretely on HP, a specific subgroup of SL2QP, which you can write down and which arises from the multiplicative group of a certain definite quaternion algebra. Okay? And I want to, okay, so we have this, and then moreover, if we have our elliptic curve E over CP, we have this uniformization by the Jacobian, and we want to understand this somehow analytically over CP. Now, if I take the Néron differential on E and I pull it back to this J or to the upper half plane, I expect to get a differential form on HP which is invariant under gamma and is rigid analytic, whatever that means, on HP. So I'm going to begin by telling you what are rigid analytic functions and rigid analytic differential forms on HP. Okay, so what is a rigid analytic function on HP? It's simply a function. I'll give you kind of a definition. A rigid analytic function on HP is a function f taking values in CP whose restriction to every good subset, and the technical term for good is aphanoid, is a uniform limit of rational functions with poles. So to every good subset A is a uniform limit of rational functions with poles outside A. Yeah. So what do I mean by uniform? I just mean that there's a norm on the space of functions on A, continuous functions on this aphanoid, which is simply the sup norm, of course, in the P-Adic topology, and you take uniform limits of rational functions. Now, what is an aphanoid? A typical example of so an aphanoid is a subset of P1CP, which is defined, so to speak, by kind of closed conditions. So the prototypical aphanoid is the set of Z in CP whose P-Adic valuation is less than or equal to 1. So this is sort of the analog of the closed unit disk in P1CP. Okay, that's a sort of typical example of an aphanoid. Now, this aphanoid is contained in P1 of CP, okay, but it's not contained in HP because it contains points on the boundary, okay? So to get aphanoids in HP, you could do something like this. You could take the closed unit disk and then also delete from this closed unit disk the various residue disks of the points in P1QP that you've that you want to leave out. So you could also take the z's for which z minus a is greater or equal to 1 for a equals 0, 1, up to p minus 1. And if you do that, you've sort of thrown out all of P1QP. So the picture of this aphanoid, and that's sort of a typical example of an aphanoid in HP, is, so it looks like this kind of closed unit disk, and then you've removed some open disks centered around some integer points. So here I'm making the picture for p equals 2 of a typical aphanoid. It would look something like this in the P-Adic upper half plane. Okay? So these are sort of points in CP which are integral and do not reduce modulo the maximal ideal of the ring of integers of CP to any of the rational points for p equals 2. Okay? That's a typical example. And then you can kind of thicken a little bit these aphanoids by enlarging the radius, so to speak, and then you can then you sort of add certain annuli. And basically the P-Adic upper half plane can be covered by these aphanoids, sort of various translates under the action of SL2 of QP of these basic aphanoids glued along these annuli. So you get a very nice combinatorial description of the P-Adic upper half plane as being covered or paved by these aphanoid subsets. And on each of these subsets, you can, if you look at the space of rational functions, so this, I mean the functions which can be written as rational functions with poles outside the aphanoid, then, and you take the completion relative to this, so of course that's equipped with a norm, which is sup norm, and you take the completion, you get the space of rigid analytic functions. Okay? And I don't want to go too much into the general theory since I don't have much time. So a boundary measure, a measure on P1QP is simply a finitely additive function. So let me call it mu so it's something in the dual of the space of continuous functions on P1QP, or equivalently, it's a finitely additive bounded function from the set of all compact open subsets U of P1QP to CP. That's a measure. And if you have a measure, you can write down, so if given mu a measure, so given mu an element in the space of measures on P1QP with values in CP, you can consider the function on HP defined by integrating the kernel 1 over z minus t against the measure d mu of t on P1QP. And because z is a point in the upper half plane, you see that this function is a nice, if you fix z, this is a nice continuous CP valued function of t, and when you integrate, you get a rigid analytic function on HP. And it's not hard to see that because you can just use it. This is by the definition of Riemann sums. This is just the sum. I take the limit over all covers. You know, I write P1QP as a union of compact opens C alpha. Okay, and I take the limit over all such finer and finer covers of the Riemann sum. So sum of 1 over z minus t alpha times mu of, maybe I'll write this u alpha. Okay, so I write P1QP as a disjoint union of compact opens u alpha. Then I take the mu of u alpha divided by z minus t alpha, where t alpha is just a sample point in u alpha. This is just the usual Riemann sum, right? And these are finite sums for each thing. So these are rational functions which have poles on the boundary, and therefore those poles certainly lie outside any aphanoid subset of the upper half plane. And so this gives you a perfectly good rigid analytic function on HP. Okay? Now, the important thing for us is that if you take a measure which is invariant under gamma, so if you look at this collection of measures on P1QP, which are invariant under the action of gamma, that's what I'll call So I've given you a map which associates to a measure on P1, on P1 of QP with values in CP, a rigid analytic function on HP. Okay, I'm not saying anything about the surjectivity of this map. But if I take now the gamma invariant measures, then I get rigid analytic functions which have a certain invariance property under the group gamma. And what I get is actually rigid analytic differentials on HP mod gamma. And so that's an exercise. It's a fun exercise, actually, to prove that. So the assignment is you associate to mu this f mu of z, which I wrote down here, dz. So this function f mu of z by itself is non-invariant under gamma. If you write down the transformation property using the gamma invariance of mu, you'll find that it transforms like a modular form of weight 2. So you'll find that f mu of az plus b over cz plus d is cz plus d squared f of z for all matrices A, B, C, D in gamma. And that means that this is behaving like a modular form of weight 2. So that, and in fact, this is an isomorphism. So that I'm not proving to you. It's kind of late in the day. So that means that we have a very explicit control over the space of rigid analytic differentials. It's enough to understand these gamma invariant measures. And I think that maybe Matt Greenberg will say a little bit more about that this afternoon. This is a very concrete object. This is a finite dimensional QP or CP vector space, which, when gamma comes from a quaternion algebra, is equipped with a natural action of Hecke operators. So equipped with a Hecke action. So in practice, if you have an elliptic curve over, in this case, over Q, but I mean over your totally real field, what you begin by doing is working with this explicit finite dimensional space, isolating the one-dimensional eigenspace for the Hecke operators, which corresponds to the measure which is going to give you the form of weight 2 associated to the elliptic curve. And then you can actually compute analytically with the elliptic curve. And this works, this extra structure somehow compensates for the fact that Shimura curves don't have cusps, and therefore there's no Q expansion. From a computational point of view, these measures are almost as good as Q expansions, and I think that Matt Greenberg will explain that more this afternoon. In fact, to illustrate that, I'm going to say one last thing about them. I'm going to explain to you how you can integrate now. I mean, because after all, if you want to define the modular parameterization by P-Adic analytic means, you need to be able to take integrals of these differential forms. And so you need to be able to integrate rigid analytic differentials. And there's a theory of P-Adic integration, which in generality is due to Coleman, although I'll give you a very naive presentation of it in the last 2 minutes that I have, or that I'm taking. So you have this sort of Coleman integral, which is simply the following thing. So you want to integrate from 2 points, tau 1 to tau 2, the rigid analytic modular differential associated to a measure mu. You want to write the integral from tau 1 to tau 2, f mu of z dz. And this is just, by definition, if you want, the integral over the boundary of the P-Adic logarithm of z minus tau 2 over z minus tau 1 d mu of, let me use t rather than t minus d mu of t. And to justify that, to justify this definition, so here you have to choose a branch of the P-Adic logarithm. So you choose a logarithm from Cp star to Cp. And there are many choices, but on the open unit disk, or on the open unit disk centered at 1, the logarithm is uniquely defined by the usual power series for the log that you know well. And then you have to kind of choose a uniformizer, an element of positive valuation for which the you decree that the log is 0. So you make a choice of such a pi. So the integral depends on this choice. Okay, and well, you see, the point is that if you want to take the integral from tau 1 to tau 2, f mu of z dz, that's the same thing as, this is just the integral over P1 QP of this measure d mu of t against z minus t. So you're expressing your f mu of z as a, as a d mu of t, exactly. So you're expressing your form as a limit of rational functions. And we all know how to integrate rational functions. Well, how do you integrate 1 over z minus t? You can do that provided you have a logarithm. And we've chosen this P-Adic logarithm in this way. And so you just say, you decree that the integral of 1 over z minus t is log of z minus t. And so here you sort of formally interchange the order of integration. And this becomes the integral for P1 QP of the log evaluated at these two endpoints, right? So you get this. So integral from tau 1 to tau 2, 1 over z minus t, d mu of t. I guess I should put a dz here. And there's a dz there too. And then this, sort of by fiat is this, okay? So that's sort of how I defined it. But okay, this is not completely satisfying because you have a, you've made a choice, which is not completely natural, namely this P-Adic logarithm. So if you want to make things completely canonical and well-defined, then you can do that in a special case. So suppose that mu belongs to the space of measures on P1 QP with values in Z gamma invariant. So this might seem a bit special, but it turns out that when you look at this vector space of measures and you diagonalize in the direction of Hecke operators, if you have a system of Hecke eigenvalues, which is integral, such as would be coming from an elliptic curve, for example, or such as come from an elliptic curve, then the measure you get actually takes values in Z, or can be scaled so that it takes values in Z. And then you get something a little bit more structured, and you can define what's called the multiplicative integral from tau 1 to tau 2, f mu of z dz, by taking the multiplicative integral over the boundary, not of the log of, not of this log, but simply of the function t minus tau 2 over t minus tau 1. And what do I mean by the multiplicative integral? Well, I replace in the definition of the integral as a limit of Riemann sums, I just formally exponentiate and write down the Riemann products. So I just do the same thing as here. I take the limit over finer and finer coverings of P1 QP by U alpha. Instead of taking a sum, I take a product. And now the thing I want to do is t minus tau 2 over t minus tau 1 to the power mu f of U alpha. And here I take a T alpha, a sample point in U alpha. And you do this over finer and finer coverings, and you get a kind of Riemann product, which is, and the good thing about this thing is that it's a canonical invariant in CP star, which is associated to the degree 0 divisor tau 2 minus tau 1. It doesn't depend on choosing a P-Adic logarithm. And now I can sort of state the main point that I wanted to make, is that if you look at this modular parameterization phi e, and you want to deal with it analytically, you want to think of it as a map on degree 0 divisors on HP, well, what's phi e of the divisor tau 2 minus tau 1? Well, you just take this multiplicative integral from tau 2 to tau 1, or I guess from tau 1 to tau 2, of f of z dz, and f you've computed by sort of dealing with these measures and writing down the... So you take this multiplicative integral, which you can write down in terms of the boundary measure in a completely explicit way. You get an element in CP star. It turns out that this element is only defined up to a certain period, a certain multiplicative period, which is the Tate period of the elliptic curve. And now if you take the Tate uniformization of it, I mean, it depends on, if you modify this by a principal divisor, you would get some power of the Tate period. So if you now take the Tate uniformization of this element in CP star, you get an element in E of CP. So yeah, is equal to that. So you get this phi Tate. This is an element of E of CP. And that's the analytic formula for the rigid analytic uniformization, I mean, for the modular parameterization by Shimura curve coming out of the theory of Cherenek-Drinfeld. this formula. E is the elliptic curve I had before. Okay? So I had an elliptic curve, which was a quotient of my Shimura curve, or its Jacobian, right? The pullback of the integral differential gave rise to a modular form of weight 2 on this quotient, which I thought of as a rigid analytic differential on HP mod gamma for an explicit gamma. Even though it's hard to write down this map explicitly, it's in most cases impossible, practically, you can still deal with this rigid analytic differential by looking at the space of measures and diagonalizing the Hecke action. And so this elliptic curve is the one which is associated with the system of Hecke eigenvalues I used to cook up this mu. So that's the recipe. Okay, and that's sort of the main formula you need to keep in mind. Matt will be showing this afternoon more. We'll be going over more details of how you actually use this to compute. And the reason for insisting on this computational theme is that in tomorrow's lecture, we're going to try to go a little bit beyond Heegner points and try to study structures which we don't understand completely yet, but where we can get explicit formulas by sort of mimicking this construction in other settings. Okay, so I apologize for running over time. Thanks.